In the first example, we have a piston cylinder device that has a gas at a pressure of 100 kilopascal. The piston has a mass of 5 kilogram and a diameter of 12 centimeter. Pressure of the gas is to be increased by placing some weights on the piston. Determine the local atmospheric pressure and the mass of the weights that will double the pressure of the gas inside the cylinder. Okay, so first of all, we remember these type of questions are questions where we have to sketch a free body diagram and show the forces acting on the piston, because remember I said in the class that piston has to be in balance, right? So it is not crashing down, so it is in balance. So the forces acting on the piston has to be balanced by the upwards that are acting on it, has to be balanced by the forces that are acting from the bottom, right? So what we can do here is write the force balance on the piston before we put the weights on. Okay, because before we put the weights on, we know the pressure is 100 kilopascal, and we know the forces acting downwards on the piston are atmospheric pressure, due to the atmospheric pressure and due to the weight of the piston. Then this has to be balanced by the pressure of the gas, right? So let's first write the force balance on before we put the weights. Okay, so we can first sketch actually, right? So if this is our piston, right, there is atmospheric pressure acting on it, and then there is the weight of the piston, right? And then this is balanced by the pressure of the gas. Okay, but of course pressure, we have to represent it in terms of force, right? It is not the force directly. We have an equation for it. We know that pressure is equal to force over area. So in the force balance, since it is a force balance, we need to write all pressures in terms of the force. So we need to do that by multiplying pressure with area. Okay, so the pressure the force due to the pressure of the gas, we can write it as pressure of the gas, right, is balanced by we delete that, multiply this with the area. This is the force due to the gas pushing the piston upwards, and this is balanced by the weight of the piston. Weight is already a force. Remember, it has the unit of newtons. So basically, we just say weight of the piston plus the force due to the pressure of the atmosphere, which is pressure of the atmospheric pressure, and times the area. So we can solve this for the atmospheric pressure, because that is what we are trying to figure out, right? In the question says one of the things we need to figure out is the local atmospheric pressure. And if you analyze this equation we just written, we see that this is the only unknown here, because we can figure out the weight of the piston from the givens, area and pressure of the gas is already given. So since we have one equation with one unknown. We can solve and use this equation to solve it for the local atmospheric pressure that we are trying to figure out, right? So we can write it as, first of all, we can divide each terms to area, right? We can then say this pressure, atmospheric pressure, is equal to pressure of the gas minus the weight of the piston, which is the mass of the piston, mass of the piston, times the gravitational acceleration is what weight is, over area. Okay, so let's delete these. All right, now our equation is here. We just need to plug the numbers in, and then we need to be very careful about the units, right? So let's say we are trying to figure this out, and the pressure of the gas is given to us as 100 kilopascal, and the mass of the piston is 5 kilogram. It is better to write all the units clearly so we can see. The gravitational acceleration is 9.81 meter per second squared. Very good. Over. So they give us the area, and they gave us exactly the diameter. So from the diameter we can actually calculate, right? Because we can calculate from the diameter what the area is, because area is pi r squared, and they didn't give us the radius, they gave us the diameter. So pi diameter over 2 squared, right? Or pi d squared over 4. So with that information, I can write down the area as pi 0.12 meters squared over 4. So here they give us the diameter in terms of centimeter, in the units of centimeter, but of course, if you look at the other units in the equation, it is better if we convert that to meter, because we see that G has a unit of meter per second, right? And the units have to match. All right, so very good. So we gotta be careful about the units, okay? So if you look at here, kilogram times meter per second squared gives us Newton, right? And Newton over meter squared is actually Pascal. And the first term in the equation is kilopascal, the second is Pascal. Units have to be the same if we want to subtract those from each other, right? So either you can convert kilopascal to Pascal or Pascal to kilopascal. So that is what I'm gonna do. I am going to actually multiply this term, right, with a unity conversion ratio we talked about. So I want to cancel out the Pascal, right? We know that 1 kilopascal is 1000 Pascal, right? So this will help me to cancel out the Pascal unit and end up with kilopascal. So all I need to do is now divide this term to 1000, okay? And then I can calculate the equation. So here, if you do that, you're gonna end up with calculating atmospheric pressure to be approximately 95.7 kilopascal. Okay, now very good. This is the first thing they were asking in the equation. In the question. So the next thing they're asking is the mass of the weights that will double the pressure. Right now we have to write another force balance. In this case, the pressure of the gas has to be doubled, which is 100 times 2, 200 kilopascal. Right now, we need to add in our free body diagram, we need to add also the weights of the weights, right? This will be, so downwards forces acting on the piston's weight, the weights weight, and then the atmospheric pressure, which has to be balanced by the pressure of the gas. So this, which will cause it to increase its pressure. Remember, because I told you when we are thinking about how the pressure of the gas inside the piston cylinder device will change, it will only change if you add extra weights on top. If you never add extra weights on top, nothing will change the pressure of the gas, because like what I'm saying is, even if the volume is doubling, I mean, nothing is going to change in terms of the pressure of the gas, because this is a force balance. And the only way the pressure of the gas is gonna change is if you add extra weight, extra forces on top of the piston. So with that, let me create a new page here, and we can now write another force balance. Okay, so we know the pressure, let's go back to black. Pressure of the gas, right, is balanced by the atmospheric pressure plus the weights of the piston and the weights of the weights, which are already forces, so I don't have to worry about those. So I mean, when I mean that I don't need to multiply them with area. So if I rearrange this equation and divide each term to the area, it is gonna be pressure of the gas, atmospheric pressure, plus mass of the piston plus mass of the weights times gravitational acceleration over area. Okay, let's see which terms we know. Here they said this is going to be 200. We have calculated this. We can calculate this. This is known. And the piston's weight is given, the mass is given. The only thing we don't know, the mass of the weights, right? And from here in this equation, looks like that is the only unknown. So that's good. And from this equation now, we should be able to solve it. So now all we have to do, plug in the numbers and solve it for the mass of the weights, okay? So pressure of the gas is 200. Atmospheric pressure is this one, and mass of the piston is 5, plus we don't know this one, we are trying to calculate, and 9.81 meter per second squared over the area is the same way, right? Being very careful to convert it to meter. And don't forget that you need to also divide this to 1000, just because of the reasons we previously shown. So from here, basically, if you solve it for mass of the weights, it is going to be 115.3 kilogram. Okay. So we had to calculate two things, and which one of them was the pressure, atmospheric pressure, and we calculated that. And then another thing was mass of the weights, and we calculated that. In the second example, we have a glass tube that is attached to a water pipe as shown in the figure. If the water pressure at the bottom of the tube is 107, so what they're giving us at the bottom of the tube, the pressure is 107 kilopascal. And the local atmospheric pressure is 99 kilopascal. So that means we know the pressure at this point, right? 99 kilopascal. Because that's a tube that is open to the atmospheric pressure, and the only pressure on top of that point is the atmospheric pressure. So now they're asking, determine how high the water will rise in the tube in meters. Take the density of the water to be 1000 kilogram per meter cube. Okay, so the pressure of the water in the pipe that is acting that point, right, is has to be equal to 107 kilopascal, because that's the pressure at that point, right? So it has to be balanced by the atmospheric pressure in addition to the pressure of water on top of it. Okay, and remember how we represent that. So pretty much this is also a force balance, but we need to remember which equations we use in a situation like this. So first of all, let's remember, if we erase these, how can I find the pressure at this point, right? So we start from this point, which has the pressure of 99, and when I go down, right, in a liquid, in water, in this case, the pressure has to increase. And how much it is going to increase is represented with the term, remember, density times g, gravitational acceleration, times the height of that liquid, right? So that has to be equal to 107 kilopascal. That has to be what is the pressure of that water in the pipe, so that it is balanced by that, right? So basically we can write this equation, which is the atmospheric pressure plus, when I go down, when I go deeper in a liquid, the pressure increases, and we remember how much it is increasing is represented by density of that liquid times the G times the H, right? This has to be equal to pressure at the bottom of the tube, which is, let's say, bottom. So this is our equation, and all we have to do here again, plug in the numbers, being very careful with the units. And here what we are trying to calculate is the height. Seems like this is given and known, and we are trying to calculate this. This is given to us, and this is given to us. So all we have to do is plug in the numbers. Let's first solve it for the H, because that is what our goal is. So atmospheric pressure, I'm sorry, not this. Pressure at the bottom minus the atmospheric pressure over density times gravitational acceleration. So pressure at the bottom is 107 and atmospheric pressure is 99. Both are given at kilopascal. Then we have the density 1000 kilogram per meter cube. And then we have the gravitational acceleration, which is 9.81 meter per second squared. So the height that we are trying to calculate has to be in meters, right? And it looks like in terms of our units in the equation, that's what we are going to find out. The units will be in meters. But we need to be careful because we know kilogram meter per second squared is Newton, and Newton over meter squared is Pascal. So looks like we can convert the numerator to Pascal by multiplying it with the unity conversion ratio of 1 kilopascal is 1000 Pascal, right? And this will help us to work with the same units, which at the end, when you calculate it, the height should be 0.82 meters. The gauge pressure in a liquid at a depth of 3 meters is read to be 42 kilopascal. Determine the gauge pressure in the same liquid at a depth of 9 meters. Okay, so let's say we are at a depth of 3 meters, and at that point the pressure is, let's say, 0.1, right? 42 kilopascal the gauge pressure is. And they ask, what about if we are at a depth of 9 meters? Let's say that is 0.2. What is the pressure, right? So if we remember what exactly is a gauge pressure, remember absolute pressure is equal to atmospheric pressure plus the gauge pressure, right? And now what we are talking about here is, let's say this was an ocean surface, right? And at this point, of course, there is some atmospheric pressure acting on that point or this point, right? And as we go deeper in the ocean, the pressure is increasing, right? So the pressure at point 1 is P1, let's say. And how do we find the gauge pressure is we actually subtract atmospheric pressure from the absolute pressure. So if you look at the pressure at point 1, how we can calculate it? We can actually calculate it by saying, okay, at this point it is the atmospheric pressure, but as I go deeper, I need to add the pressure due to this extra weight on top of that point, right? Which is density times G times H1. Let's say this is H1 or 3 meters. So this is equal to the pressure at point 1, or in other words, the absolute pressure. But this term turns out to be absolute pressure minus the atmospheric pressure. In other words, this is the gauge pressure. So P gauge, let's say this is P pressure, gauge pressure at point 1, right, is equal to density times G times H1. Okay, so similar to that, so let's rewrite it again here. P1 is equal to density times G times H1. And then therefore the gauge pressure at point 2 has to be therefore density times G times H2, right? Now what they are giving us is the gauge pressure P1 as 42 kilopascal. They are giving this to us, and we know density, okay, and then G, and then this is at 3 meter. Now they're asking what is P2 or the gauge pressure at point 2. These two terms has to be the same, density and G has to be the same. Of course, the gravitational acceleration doesn't change, and it is the same liquid or substance what we are going deeper into, right? So the density is the same. So this depth we are now going to is 9 meters. So basically they're asking us to find what is the gauge pressure there. So I can solve this equation for the term density times the gravitational acceleration, which gives me 42 kilopascal over 3 meter. And since this is the same in this case, I can just plug it in to solve for P2. And from here, you can simply find the gauge pressure at point 2 to be 126 kilopascal. So in this question, we have a pressure cooker. And in the pressure cooker, we have a metal piece called petcock that sits on top of the opening and prevents steam from escaping until the pressure force overcomes the weight of the petcock. So again, this type of questions are related to drawing the free body diagram of the petcock and sketching what forces are acting on it, and assuming the petcock is in balance and the pressures are acting on it, we need to write a force balance on it. And let's sketch it. So let's say this is the petcock, and on top of it acting is the atmospheric pressure, right? At this point. And we are given the area of it, 4 millimeters squared. And we are also given the atmospheric pressure, 101 kilopascal. And we are also given the operation pressure of 100 kilopascal. It's the gauge pressure. That's what the problem statement says. So remember what gauge pressure is. It is absolute pressure minus the atmospheric pressure. So now let's look at the free body diagram here. The forces that are acting on the peacock is so the atmospheric pressure is pushing it down, right? And the pressure of the gas inside, which is the absolute pressure of the gas, or I guess the steam, we can say, is pushing it upwards, right? And then there is also the weight of it acting downwards, so which is equal to mass times gravitational acceleration. So if we write a force balance here, let's look at it. Pressure inside times the area, right, equal to the weight and plus atmospheric pressure times the area. Remembering again, pressure is force over area. And if we are writing a force balance, we need to write pressure in terms of force. For that, we need to multiply area with the pressure given, right? So after we write down the force balance, we can divide each term to area, pressure, weight, which is mg over area. Now, if you look at it, what happens here is the pressure, the absolute pressure within the pressure cooker minus the atmospheric pressure gives us, remember, the gauge pressure. And gauge pressure becomes directly equal to mg over area. Now they give us the gauge pressure. They give us the gauge pressure to be 100 kilopascal. Okay, and for that reason, from here we can use it to plug into our equation, but let's see what they're asking for. It says determine the mass. Okay, so we are going to determine this one, right? So if we solve it for the mass, let's say P gauge times area over G should be equal to the mass. Okay, now we have a formula how to calculate the mass, and this came from basically the force balance, and also from the knowledge that absolute pressure inside minus the atmospheric pressure gives us the gauge pressure, and the gauge pressure is already given. And from that information, we now know what is the equation we need to use. So let's plug in the numbers. 100 kilopascal. Area, let's see what they have given us. They have given it a 4 millimeters squared. So we need to convert this to meters squared. And it is 4 times 10 to the power of minus 6 meters squared over 9.81 meter per second squared. Okay, now the units are, again, we need to be careful, right? We need to end up with a unit of kilogram. So what I would do is convert this kilopascal to pascal. Okay, to do that, remember, you need to multiply this with 1000, because 1 kilopascal is 1000 pascal, right? So if you do that, if you multiply this with 1000, it will convert it to pascal. And once you do that, let's take a look at the units, okay? So pascal is Newton per meter squared times meter squared over meter per second squared, right? And we also know Newton is kilogram meter per second squared. So meter second squared, they cancel out. We end up with a unit of kilogram. Now it looks like it makes sense. All right, so you need to be very careful with the units and doing the right unit conversions. A manometer containing oil is attached to a tank filled with air. Okay, so we are using manometer to measure, I think, the pressure of the air. If the oil difference between two columns of that manometer is 80 centimeter and the atmospheric pressure is 98, determine the absolute pressure of the air in the tank. Okay, so we have tank, and we are filled with air, right? And we are attaching manometer. to calculate the pressure, right? So due to the pressure of the air, which is its absolute pressure, right? The liquid will be pushed on the other side, and this is the difference in that levels. They say it is gonna be 8 centimeter. Okay, so this is the oil. The manometer uses oil as a liquid. Okay, so we know that the pressure at this point is the atmospheric pressure, and the pressure at this point and the pressure at this point are equal to each other. So because we are talking about the same horizontal line connected with the same environment, which is oil, so since this is the same horizontal line and they are connected with oil, the pressure there has to be the same. Okay, so that's why if we look at the pressure at this point, it is equal to the pressure of the air. The absolute pressure of the air should be equal to that point, the pressure at that point. But we know, let's say 1.2, point 1.2, they have the same pressure. But how can we calculate the pressure at point 2, right? We need to add this term, density times G times H, which is 80 centimeter, to find the pressure at point 2, in other words, at point 1, or in other words, the pressure of the air, right? So let's basically do it, right? They already given us this to be a 98 kilopascal, and we just need to plug in the numbers for this term. So 98 kilopascal plus the density is for the oil 850 kilogram per meter cubed, okay, times 9.81 meter per second squared, times the distance is 80 centimeter, means 0.8 meter. Now this is in the units of Pascal, remember, because kilogram meter per second squared, again Newton over meter squared is Pascal. This is Pascal, this is kilopascal. What I would do is multiply this with a unity conversion ratio of 1 kilopascal is equal to 1000 Pascal. This will convert this to kilopascal. And then we can sum up those two terms, which should give you approximately 105 kilopascal. Okay. So remember, the absolute pressure is always bigger than the atmospheric pressure. So atmospheric pressure was 98. And now we are able to calculate the absolute pressure of the air to be 105 kilopascal. Another manometer question. In this manometer, we have two fluids, fluid A and fluid B. I think one side of it is open to air, atmospheric pressure, and other side is attached to a system where we are measuring its pressure. And seems like the pressure acting on the other side is P1. Okay. And this side is the atmospheric pressure. So they're asking if the atmospheric pressure is 90 kilopascal, what would be the absolute pressure measured, right, at P1? What is the pressure P1 basically? Okay, so again, we can start at any side, either P1 or the atmospheric pressure side. And remember, as we go down, we are going to add terms because the pressure has to increase as we move down. And as we move up along the manometer, the pressure has to decrease. So we subtract some terms, right? But first of all, remember what is specific weight, and the formula for the specific weight was density times gravitational acceleration. So they are directly giving us density times gravitational acceleration for a fluid A and B instead of just giving the densities of them as a separate term from the gravitational acceleration. They prefer to give it as a specific weight for each fluid. And if we start from this point, right, let's set point 2, and this point we can make this point 1. Obviously, the pressure at point 1 is equal to the P1, and the pressure at point 2 is equal to the atmospheric pressure. Now what we can do, we can come to this point, okay? We can start from point 2, which is equal to the atmospheric pressure. Now as we move downwards and coming to this point right there, the pressure has to increase, right? Because as we go deeper, we know the pressure increases. How much increases? We need to add this term, density times G times H1. And in this case, H1, let's say it is 15 centimeter, okay? Now, as soon as we find the pressure at this point, we also find the pressure at this point because they have to be equal. They are connected with the same fluid and they're on the same horizontal line. It turns out once you find the pressure at this point, you also finding the pressure at this point because both of those points are connected with the same fluid and they are on the same horizontal line. So by just calculating the pressure at this point, we're automatically calculating the pressure at this point. Right now we have that, okay? But we need to continue. We need to now continue going down, okay? Coming to this point. Okay, so then let's add that term, right? As we are going down, let's say H2. Since we moved this much, this should be equal to 5 centimeter. Okay, this. Okay, from the sketch, right? From the given figure, we were able to figure those out. And once we come to this point, automatically we know the pressure at this point because they're on the same horizontal line connected with fluid A. So now we actually have the pressure at 0.1. So basically that is what we are looking for. Right now, I think we should be able to plug in the numbers because they already given us the atmospheric pressure to be 90 kilopascal. And they give us this term for fluid. So first we've moved in fluid B, right? This should be for fluid B, and then this should be for fluid A. Let's look at it. For fluid B, what is the density times G? It is 8 kilonewton per meter cubed times H1 is 15, which makes 0.15 meter, plus specific weight for fluid A is 10 kilonewton per meter cubed times 0.05 I'm sorry, I think there is something wrong here. Yeah, I'm gonna show you what is wrong. Give me 1 second. So we write down this, right? Here they say 100, and here in the sketch it is 10. It should be 100 here too, right? Okay, so we add one more 0, and we finalized our equation. And all we have to do now, calculate from this equation, but being very careful with the units. Okay, so this is kilopascal, therefore all other terms have to be kilopascal. So what we have here is kilonewton per meter squared. It is actually kilopascal, so we can keep in mind that 1 kilopascal is actually 1 kilonewton per meter squared. 1 pascal is Newton per meter squared, right? 1 Newton per meter squared. So therefore, there is nothing to change here in terms of units. Everything is in terms of kilopascal. We can sum those up and it should give you 96.2 kilopascal. Okay. Both a gauge and a manometer are attached to a gas tank to measure its pressure. If the reading on the pressure gauge is 80 kilopascal, determine the distance between two fluid levels of the manometer. If the fluid in the manometer is mercury and if it is water, what will be the distance? Okay, so let's remember the equations we have. First of all, the pressure at this point, we know that it is the atmospheric pressure, right? And pressure here is the pressure of the gas. And that pressure in that point is equal to the pressure at this point. So pressure of the gas, or the absolute pressure of the gas, is actually equal to, we can write it we need to add this term to the atmospheric pressure, right? Now, what is the equation for the gauge pressure? Remember, gauge pressure is basically the absolute pressure minus the atmospheric pressure. Okay, so if you look at it, therefore, if you write it so basically the gauge pressure is equal to density times G times H, right? Now, they are giving us this gauge pressure, and the gauge pressure is 80 kilopascal. Okay, so from there, this is given, this is we know, and we can calculate what the heights are going to be for different fluids. Okay, so let's do it. So the gauge pressure is, or let's solve it for H, right? H is equal to the gauge pressure over density times G. Okay, now if this is for mercury, the pressure at the gauge is 80 kilopascal over density for mercury is 13,600 kilogram per meter cubed times 9.81. Okay, but we need to be very careful because numerator is kilopascal, denominator in terms of pascal, because remember kilopascal is kilonewton per meter squared, and what we have in the denominator is kilogram meter per second square. It's Newton. So we need to multiply this with 1000 so that we can convert it to Pascal, the units of Pascal. So therefore, from this, you should be able to calculate H to be 0.6 meters if it is mercury. Okay, we can repeat the same process for basically the water, and for water the gauge pressure is the same. Okay, and the density now is 1000. We are not forgetting our unity conversion ratio. Right, and this should give us H to be 8.16 meter. So you can see that why they might choose to use different fluids in a certain manometer, because the heights or the differences in the levels will be at different values. That's why. Okay, so in the case of the mercury it is 0.6 meters, and in the case of the water it's 8.16 meters. Okay, all right, so another manometer question. In this case we are given the gauge pressure of air as 80 kilopascal, and we notice there are 3 different fluids here. We are dealing with water, mercury, and oil, and we are asked to calculate H, the height of the mercury column, this part, and what we are given is SG. SG stands for specific gravity. Specific gravity is basically the density of that liquid or fluid over the density of the water, and those are given to us. So similar to the example we have solved previously and also in the class, that remember we just need to start from one point, and as we move downwards we keep adding the terms because the pressure is increasing, and as we move upwards we need to subtract the terms because the pressure is decreasing, right? So first of all, pressure at this point is, let's say, pressure at point 1, and this is pressure at point 2. This pressure at point 2 is equal to the atmospheric pressure, and pressure at point 1 is equal to the pressure of the absolute pressure of the gas. Okay, so let's say we start from point 1, okay, like we did for the example in the classroom. So pressure at point 1, if I move downwards from that point and come to this point now, the pressure has to increase. And how much it's gonna increase? We are adding the density of water, since we are moving in water. Density of water times G times the water's height, which is in this case 30 centimeter. Okay, but since we are at the same horizontal line, this point and this point, they have the same liquid, right? Then they should have the same pressure. And Similar to that, if you extend this horizontal line, this point and this point should also have the same pressure because they are also connected with the same liquid, right? So with that information now, by calculating this term here, we are able to calculate the pressure at this point, right? But at that point now, to reach point 2, I need to move upwards in mercury, in the distance of h, right? So if I move upwards, I need to subtract that. Density times mercury, G, H, mercury. H mercury is basically H, right? So we come to this point. Now we are moving upwards again to reach point 2, but this time we are moving in oil. We again need to subtract because the pressure is decreasing, right? So we're going to say the density of oil, G, H oil, okay, which is 75 centimeter. Now this should be equal to the atmospheric pressure at point 2, right? Now they are giving us the gauge pressure 80 kilopascal for the air, which is the pressure at point 1. But I'm sorry, they are giving us the gauge pressure 80 kilopascal, and the pressure at point 1 is the absolute pressure of that air. So remember how we calculate the gauge pressure. Gauge pressure is basically the difference between the absolute pressure and atmospheric pressure. So if I actually rearrange this equation, I can rewrite it in terms of P1 minus the atmospheric pressure is equal to, let's erase this. If I rearrange it, these terms going to the other side, right? So it's going to be oil mercury so directly, therefore, the difference between the absolute pressure of air at point 1 minus the atmospheric pressure is actually the gauge pressure, what they are giving to us. Okay, so far so good. Now let's also take a look at what they give us. They gave us the specific gravity for oil and mercury instead of their densities. So remembering specific gravity is equal to density of that fluid over the density of water. Therefore, if I want to calculate the density of that specific fluid, I need to multiply its Sg with the density of water, which is usually taken as 1000, right? 1000 kilogram per meter cubed. Okay. Now, therefore, what I can do in these equations is instead of the density of mercury, I can write Sg given to me for mercury, which is 13.6, right, times the density of water. So for example, I can plug this in here. And for oil, I can do the same thing, right? Sg given to me for oil times density of water. So let's plug those in and see what we're going to get, okay? So the gauge pressure is equal to Sg for the oil times the density of the water times G times, or this is not a good way of writing things. I'm sorry. So Sg times density times G times H oil plus Sg mercury times density times water GH mercury minus G water and raw water density GH water. Okay. All right, so after that, when we look at it, seems like there are similar terms in each of those terms, which is the water times the gravitational acceleration, right? So we can now rearrange this equation again. I can say gauge pressure over density of water times G should be equal to Sg of the oil times the height of the oil plus Sg times the mercury times the height of the mercury and subtract the height of the water, right? So let's now take a look at what they have given us. They have given us this, 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 this. They asking for this one, right? So then there's only one unknown, and we can just plug in the numbers, and being careful with the units, we should be able to calculate it. So let's go to a new page here, right? Because I think, yes. So new page, just remembering our equation, okay, rewriting the same equation. Okay. Okay, let's plug in the numbers. So gauge pressure was 80 kilopascal. Density of water is 1000 kilogram per meter cubed. G is 9.81. Oil Sg is given to us as 0.72. And H is given to us as this. Sg doesn't have a unit because you are dividing density to density, right? So it doesn't have a unit. The height of the oil is 0.75 meter. They give it us in centimeters, but we convert it to meters. Now it is 0.75. All right, we add now this term, which is for mercury, it is 13.6 times the mercury's height, and we subtract 0.3 meter. Okay, so seems like from this we can able to calculate this one. All right, but let's take a look at the units, making sure. So I can see that seems like there will be here, the unit on this side is meters. So basically, looking at this is the denominator seems like it is in terms of Pascal, and I need to convert kilopascal to Pascal. So what I would do is again convert this to Pascal with using unit conversion ratio, and now it should make sense. Okay. All right, so after doing that, you should find the mercury's height to be 0.582 meters. Okay, so there is piston cylinder device that contains a gas at 180 kilopascal. And the atmospheric pressure outside is 100 kilopascal. And the piston's area is 25 centimeters squared, which should be equal to 25 times 10 to the power of minus 4 meters squared. Determine the mass of the piston. Okay, so this is again a force balance question, right? We can sketch a free body diagram and sketch the forces acting on the keeping the piston in balance. So there is the weight of the piston, and there is the atmospheric pressure, and this is balanced by the pressure up to the pressure of the gas. Okay. And we can write down the force balance equation, remembering again the pressure is over force over area. So we need to write force, right? So we need to multiply all the pressures given with the area. Okay, so what is acting downwards has to be balanced with forces acting upwards. So basically we have the pressure force together with the weight of the piston balanced by the force of the gas. Again, dividing each term to the area, we can simplify our equation to atmospheric pressure times weight over area times the pressure of the gas. And we are given this to be 100, this to be 180. Therefore, the weight over area, weight is mg over area, should be 180 kilopascal minus 100 kilopascal, which is 80 kilopascal, right? Now, let's plug in the numbers because this is what we're trying to figure out, and this we know. So in this equation, it must be very simple to calculate the mass, right? Mass is 80 kilopascal times area over G. Area is 25 times 10 to the power of minus 4 meters squared over 9.81 meter per second squared. In this case, we again need to be very careful because this is kilopascal. So we need to convert it to Pascal. So we need to multiply this term with 1000. Okay, get rid of kilopascal and write it in terms of Pascal, because Pascal is Newton per meter squared, and in Newton we have kilogram meter per second squared. So we're gonna find the mass in terms of kilogram, right? So after we do those calculations, you should be able to find mass of the piston to be 20.4 kilogram.